signals and it propagates through the core of the fiber. So during this coupling, light signals which are being radiated above the fiber acceptance angle gets lost. So that has to be reduced. We had seen the power calculation for LED step index, then for multi. We had seen the lensing scheme for improving coupling efficiency. So next we are going to discuss the non-imaging microsphere. So the non-imaging microsphere non-imaging microsphere. So the active area or the optical source and the fiber, and between these two we have non-imaging microsphere. So that will allow the that being generated from the active area of the optical source to launch into the core alone. So on examining the non-imaging microsphere or surface emitter as shown in the figure, the assumptions made are that a refractive or spherical lens of 2.0 is taken, which is air is having refraction 0.0 and the emitting area is circular. Then the focal length can be found from the Gaussian lens formula as n by s plus n dash divided by q, which is equal to n dash minus n divided. So where s and q image distances respectively. S is the distance of the q is the image distance. N the lens, n dash is the refractive index of the outside of curvature of the lens surface. So this is a circular. Focal point for a right hand surface of the lens as shown. We need to solve s in the equation from point B. So assuming n is equal to 2.0, 1.0 and r is equal to minus RL. So then we can write focal point as s is equal to f, which is equal to 2 RL. So the focal point is located on the lens surface at a point E, as shown in this diagram. So this is a schematic diagram of an LED optical source with an microsphere lens. Your optical source, this is a microsphere lens. So this is your region. This is the H12. So here, which we want to find is there. So at a radius of RL, which is the microsphere lens radius, we'll get the focal length at point B at here. Making an assumption that n is 2.20 and n here 0. So here this n is your 0.0 is your refractive index of the lens, and this is your refractive index of the medium. This is your non-imaging microsphere. So next is the graph which illustrates theoretical coupling efficiency for a surface emitting LED with respect to coupling efficiency to diode. So it depends upon the here this emitting area. So The light signals which propagates will propagate in this direction towards B. So how till far away it can propagate is your diameter. Okay, here the radius is this. Radius of the microsphere lens. So how much amount get is your emitting area. So that in micrometer. So given in x-axis. The numerical aperture of the fiber is taken as 0.20 and A value as 25 micrometer. You can see that efficiency till 15 micrometer. You have 100 efficiency. So as the emitting area diameter increases 50 micrometer, its efficiency decreases. You can see the diameter of emission is within this region, smaller region. More when it increases, the diameter of this increases, then efficiency gets reduced. So placing the lens surface results in a magnification of the emitting area by ratio m. So m is equal to p rl square divided by p rs square, which is rl divided by rs the whole square. The equation, the optical power pl can into a full aperture angle 2q pl is equal to ps rl by rs the whole square sine square. So where ps is the total output power from the LED before the lens or without. So for fiber of a radius having a numerical aperture Na, the maximum is given by A divided by numerical aperture the whole square. If RA by square is greater than numerical aperture, if it is less than or equal to numerical aperture, it is always 1. The maximum coupling efficiency. So when the radius of the emitting area is larger than the fiber radius, no improvement in coupling efficiency is possible. So in this case, best coupling efficiency is achieved by a direct method. If the emitting area is larger than the fiber radius, we can go for a direct butt method. So based on the theoretical as a function of emitting diameter as shown, an optical fiber of having numerical aperture 0.20, 50 micrometer core diameter is best. So next is the laser diode to fiber. Or whatever we are doing is that coupling on LED, so coupling and laser diode. So the edge emitting laser have an emission pattern that nominally has a field width of 30 to 50 degree in the plane perpendicular to the and 5 to 10 degree since the angular output greater. So the laser will have an angular output distribution greater than fiber axis angle. Emitting area is much smaller than the fiber core. So we can use a spherical lens or a cylindrical lens or a optical fiber tappers. Coupling efficiency between the and the edge emitting laser diodes. So a spherical glass lens with a refractive index of 1.9, diameter ranging 50 to 60 micrometer, epochs to the end of a 50 micrometer. Diameter with the greater index fiber having a numerical aperture of 0. So the measured wave of the laser output beam would be between micrometer for near field, which is parallel to junction, degree and 60 degree for the field perpendicular to the junction, 55 degree for the field parallel to the junction. Give and coupling efficiency between 50 to 80. For this is a step index. The next is our gradient index. The index will have a core radius A and a cladding index with a constant k is equal to 2 pi by lambda. Of modes can be calculated as m square 0 to 2 n square r square of r minus n to the whole square. Where n of r is your variation of the core. With respect to r, it will vary. Number of modes that can relate to the local numerical aperture. M is equal to k square n a square 0 to 2 1 minus r by a the whole power alpha to dr. So the fraction of energy coupled fiber to another fiber is proportional to the common mode volume. So the fiber to fiber coupling. So in the previous case we had optical source to cable coupling. Now one fiber to another. So the fiber to fiber coupling efficiency is given as is equal to m com, which is your common mode volume. So m is the number of modes in the emitting fiber. So due to this fiber coupling, there could be a losses of your optical signals, which can be determined by the fiber to fiber coupling loss as LF in terms of eta f. So eta f is equal eta f com divided by me. So minus 10 logarithmic of that function fiber to fiber coupling loss. Model equilibrium has been established in the emitting fiber. The optical located near the center of the fiber as shown. So the optical power emerging from the fiber then will be at its equilibrium numerical aperture as shown in this figure. So we have an fiber core material. This is a cladding. So all modes are equally excited. So then it will exhibit during the fiber to fiber joints. Numerical aperture of the fiber will be exhibited. So when all modes are equally excited, the output beam fills the entire output. So when all modes are from fiber 1, when it is being coupled with another fiber at fiber 2, if all the modes are excited, then output will fill the entire output. So if numerical aperture equilibrium is filled, then you can, few modes are excited, then the propagation modes in the steady state will give only an numerical aperture. So that is filled in the output beam. So any queries in the fiber to fiber joints or in the power coupling schemes, you can type in. From 5 to 10 minutes of time will be given. Any queries you can type. Thank you, Sai Ganesh. Thank you, Mukesh. Since there are no queries, I proceed on to the next topic presentation. So the next topic is a continuation of the power launching schemes, fiber to fiber joints, which is fiber. So let us see what we are going to discuss in coupling. We are going to see the behavior modes which is present in the optical source, how they behave. Then we are going to see the optical beam filling with respect to the numerical aperture. We are going to see it with respect to the equilibrium of numerical aperture in previous class. At last, we are going to see the losses. So if all the modes at optical beam will fill the entire numerical aperture as shown in case of equilibrium state, only would be passed on. So in the fiber, the other fiber, the second fiber, will be having only the equilibrium numerical aperture at the central region to pass on the power which is being from the first fiber. So there could be power losses due to three types of alignments of the fiber. So this is a fiber 1, fiber 1, fiber 2, fiber 1, fiber 2. So these two fibers are being joined. So but during coupling or during joining, so there is an misalignment. So it is the core doesn't fit exactly with the core. Second fiber. So as shown in lateral axial. The next longitudinal, whereas fiber 1, fiber 2 should be coupled within each other. There is a space between them. So this type of misalignment we call as longitudinal misalignment. The third one, at angles or at bends at an angular shaped structure like this. So with respect to an angle. So one end would couple, other end would be having a gap. So these are the three types of with which we get power loss from the older fiber to the newer fiber. Let us see the axial misalignment or the lateral misalignment. So here we have the core radius of optical fiber 2. So due to this mismatching or misalignment, so the fiber which transmits the optical light will get lost into this white area. So this white area. So only the common area will for optical signals. So this is a most common practice seen in step index fibers, which gives greater power loss. When we assume a uniform model power distribution, this occurs coupled power proportional to the common area. Efficiency is the ratio of common area to the receiving face area, so which is beta f step index, beta f is equal to which is the fiber core common area divided by pi s square, core area. So next is the axial or lateral misalignment in greater index fiber. So which is coupled is restricted by the numerical aperture receiving fiber end whichever is smaller at that point. For an uniform illumination of the optical power accepted by core, which is the power that falls within the numerical aperture of that. So the optical power density P of R at a point R on the fiber end face is proportional to the square of the aperture, which is P of R is NA is numerical aperture the whole square of origin. So which can be given as P is equal to 0 to 2 pi limits 0 to A P of R into dr into d theta. So the axial or index fiber in area A1. Here the number of would be more than the receiving fiber. Will accept only one part of the transmitted power that falls within its aperture. So in area A2, numerical aperture of the receiving the transmitting fiber. So the receiving fiber will accept power in this region. So depending upon this, we can choose which region to use in your axial or lateral misalignments. Next is separation, which is end separation. So transmitting fiber core, we have a so there is a gap in between. So S is the one and fiber two, emitting fiber core and receiving fiber core. So due to this, there will be an angle being created due to the separation. So in this, so will travel. So that is your power lost. When light signals through this passes through this angle, the power is being lost. So the power is lost to a distance of x. So power is lost, and here power will be transmitted. So this is being calculated by the critical acceptance for theta c. So this plays a major role. So with optical power emitted in the ring of the width x will not be intercepted by the receiving fiber. So the loss is calculated by minus 10 log of a divided by a plus s tan theta c the whole square. Yeah, sorry for the interruption. A network issue. Joined it again. So the topic is separation or end separation. So when the fibers are being coupled in this fashion, so fiber one is emitting a fiber core, fiber two is a receiving fiber. Gap between these two is present is your S. So due to this, the transmitting optical signal which is being transmitted from the fiber 1 to fiber 2, the impulses optical signals will propagate inside this beyond. So this is lost. So the distance x is the distance from the fiber core. So their power is lost, and the remaining where the power is being coupled. So this is a longitudinal separation or the end separation coupling method. So the last fiber or the last signal can be determined by the formula LF, lost by log as minus 10 log of A plus S tan theta C the whole square. A is the radius of the core of fiber 1 and fiber 2. So S is the distance being separated. This distance is being separated. And theta C is the critical angle or the angle of acceptance. So other than the above mentioned, there are fiber related losses, so which are due to the difference in the geometrical and characteristics. There are fiber losses being, so one is depending upon the core diameter variation, one is the core area ellipticity, third one is the numerical aperture variation, third one is the refractive index profile variation, fifth one is the core cladding. So in our syllabus, we have discussed only the core diameter variation and the numerical aperture variation schemes. So this is about your fiber coupling. So any queries in the fiber coupling, you can type in chat box. 5 to 6 minutes of time will be given. If any queries, you can type in chat box for the next topic. Okay, thank you, Mukesh. Okay, since there are no queries, we'll proceed to the topic, which is fiber splicing. So kindly be awaited. We'll start. So next topic is fiber splicing. The fiber splicing is a methodology for cutting and joining of either it could be different fibers or same fibers. So which has to follow some criteria. So we'll see the criteria and the mechanism. So the fiber related loss that we had seen just now are the core diameter, core area ellipticity, which is in refractive index profile, and the core cladding. So the fiber losses are significant for different core radius and the numerical aperture, which can be obtained as in this form. Different core radius. Different. The loss is indicated by loss is A, which is equal to minus 10 log of AR divided by square. For AR less than AE. For greater than or equal to AE, it is 0. Loss is 0. So if there are different numerical aperture, so then loss due to the numerical aperture is equal to minus 10 log numerical aperture at the received the divided by the numerical aperture at the whole square. So for numerical aperture at the received less than meter. Okay, NAR is your numerical aperture, NAE is your numerical aperture at the emitter. So if the is greater than or equal to numerical aperture of the emitter, then 0. So if the fibers are having different core index profiles, different refractive indexes, so they count as LF of alpha, which is minus R into AE plus 2 divided by AE plus 2. If AR is less than E, the core of the receiver is less than the core of the, so it is 0 if the core of the receiver is greater than the core of the emitter. So next is the Fiber end phase preparation. So the end phase preparation is the first step before connecting fibers through connectors. So which is joining two fibers. So the fiber end or which you want to cut and join should be flat, perpendicular axis, it should be smooth. There are three methods used for doing this. One is grinding, second one grinding, third one polishing. So grinding require a controlled environment like a laboratory or a factory or a company is required where you can control optical fibers grinding and polishing. So in sawing we don't require that. So controlled fracture techniques that are used to cleave the fiber is shown in this diagram. You can see we have an optical fiber. We need to cleave at this point. So we have a curved form. Okay, here is the tension. There is a tension. We need we need to hit it with a scoring blade such that this is being removed. So highly smooth and perpendicular can be produced through this method. So this requires careful control of the curvature and the tension. So this curvature, this fiber and this fiber should be tightly tensioned or it should be grabbed in such a way such that the scoring blade will cleave away the optical bend. So must be taken in controlling of the curvature and the tension. Tension can cause multiple fracture and can leave a harmed. So as like this. So smooth end face with a lip, smooth surface and a hacked surface. So this tend to break. One way to avoid this is a methodology called splicing. So that there are three different that can be done, which is first one is the fusion splicing, second two mechanical splicing, third one elastic tube splicing. So let us see the fusion process first. In the fusion process, the following characteristics to be followed such that fusion can be done efficiently. One is ring effect, second core eccentricity, maintaining core eccentricity, third one fiber end phase quality, maintaining a good quality at the end of then fiber preparation quality should be maintained or coating residues should be removed. Then statistics, then electrode condition. All this that influences the. So first let us see the self-centering effect. The self-centering tendency of the fiber to form a homogeneous joint that is consequently free of misalignments. No misalignments that result that results from the surface tension of the molten glass diffusion bonding process. Core eccentricity is the fiber core, which is of great importance in splicing. Eccentricity can cause the losses of the position of the relating cores, increased splice loss due to the core offset. Next quality is fiber end phase quality. The end phase quality of fiber directly influences the splice loss. So thus when cleaving splicing, the end face of the fiber has to be cleaned and flattened and should be perpendicular to the fiber axis. So so the fiber preparation quality is that for splicing it is necessary to ensure that no damage occurs to the only core is being cut. So any damage to the unprotected glass micro cracks causing the fiber to break during handling, splicing or storage. So the entire optical fiber cable properly prepared for splicing. So if there are any contamination like dust particles, dirt, or coating residues which are contamination on the fiber or present in the V groove can lead to bad fiber positioning. Lead to fiber misalignment, which is our lateral misalignments, and can influence the fusion process extremely, like bad. Next is the fiber melting catalyst. So when the fibers are brought closer to each other, will be present, which is called as gas bubbles. So electric will not be able to weak. So when an electric arc melts the fibers, the glass tends to collapse, filling the gap, which may lead to absorption. Electrode condition. So the electrode that we use for making arcs should be should re, should have a stable fusion arc. The arc should be in electrode condition. The electrode cleaning replacement. The electrode cleaning or replacement should be done. So this is the method, fusion splice method. We have two fibers. This is optical fiber 1. This is optical fiber 2. Fiber hold. Fiber holders are put on. Micro manipulated fiber holders. Then we have an arc, electric arc welder, or a laser fusion welder, which will press this to and this gets to here a thermal bonding of two that is to be spliced takes place. So the chemical melting sometimes may produce a weaker splice that may require to produce very low splice loss. So this next is the V grooves. So here we have two fibers. So this one, this is fiber 2. So these two fibers is to be spliced. So this V grooved channel, either grooved in a silica, plastic ceramic, or a metal substrate. So V shaped structure channel. So they are bonded with an adhesive material. So the fiber ends epoxed or clamped here. Where we so then a bond is being put up near the place to be spliced. The splicing takes place. So the prepared fiber ends are but together, but is joining, or but together in a groove. They are bonded with an adhesive. The V-shaped channel is either grooved with silicon, plastic ceramic, or metal substrate. Here the splice loss depends upon the fiber splice eccentricity. Next is the splicing. So this elastic splicing is that we have two fibers. So already inserted with a larger diameter to be spliced having a diameter less than that. It automatically performs lateral, longitudinal, angular alignments. It splices the multimode fibers with losses in the range of commercial fusion splice. This requires less equipment and skill. It consists of a tube of an elastic fiber. You can see material fiber. It is a tube. There is a hole in. So capillary tube size less than the fiber radii. We have an axial alignment. This fiber into the. So the internal hole is of a smaller diameter as compared to the fiber and is tapered at the two ends for easy insertion of the fiber. A wide range of fiber diameters can be sliced. To be spliced might not be of the same diameter, still its axial alignment will be maximum. So we have the taper openings.